Good morning, everybody. Nice to see a full class here today. If you could start with some green check marks and to make sure everyone's with me, and then we'll get going. We'll get started. As well, if there's anything from the previous unit, so unit 7 that you had issues with, couldn't get, something in the learning guide, whatnot, let me know in chat and we can go through any of that stuff. But if not, we're going to jump into vectors and displacement, which is the beginning of chapter 8, which is kind of our introduction to motion. So two chapters on motion, and that's it. I wanted to show you guys one web page I kind of stumbled across in related to some of the material we were talking about before, and then we'll jump back into this stuff. So a few of you guys are typing, so I'll just give you a chance to finish typing if you had any questions or anything like that. But if not, we'll be on Unit 8 and 9. Do I think we'll get through Unit 8 this week? No. I think there's 3, well, I shouldn't say that. We might. It's not like terribly difficult stuff, and there's not a lot of material. We're going to have class twice this week. The following week is kind of a weird one because we have the long weekend, and then the 24th is a Tuesday after the long weekend, which is a non-instructional day. So all of the teachers in the district are getting together to discuss the new curriculum. So you guys will only have 3 days of class, or I guess 2 days of class because you don't have class on Friday. And you'll have social studies one day, and then I think Mrs. Ward's taking you guys to the museum or something like that. So we'll have 2 blocks of science this week. We won't have any science the following week. And then we're actually into June already, which is crazy. So Unit 8 has 3 lessons in it. I don't know if we'll be able to get that done in this week. We might. I don't want to push it. There's no point in rushing. Then Unit 9 has 2 lessons in it. And that's basically it. There's 5 sort of lessons left. We'll spend some time doing some review. We'll spend some time looking at a review of like all of the different units we've done. And then after that, you guys will write your provincial and the year's done. So we're definitely in the home stretch now, guys. And it's great to see a bunch of you in class. So we'll just keep plugging away. All right, so just got to your question, Abby. One question is about dating, so like radiometric dating or radioactive dating. Can we use carbon-14, uranium-235, or potassium-40 depending on the age and composition of the item? Yes, so the problem with carbon dating is it's only good for 5,730 years for 1 half-life. So if we multiply that by 10, because generally we can get about 10 half-lives out, 5,000 times 10 is 50,000. So if we wanted to date something that had carbon in it that was older than 50,000 years, then we wouldn't be able to use carbon-14 dating as well. If it was something that didn't have carbon in it at all, like maybe you have a rock sample. I was just reading an article about some rocks that were discovered in the Australian outback, I think, and kind of a weird layer of soil or something, and there are these meteorites, and they were really old, obviously, so meteorites wouldn't have any carbon-14 in them, and if they did, it would all have decayed into nitrogen. So basically you use something that allows you to kind of be in the date range you're hoping for, and something that has some of the composition that you're looking at. So you wouldn't use carbon to date like a rock, because we wouldn't be able to find carbon in a rock. Rocks are generally quite old. So you'd want to use something like uranium or potassium, just depending on it. So if you, I'll just grab my data book because I don't have these numbers memorized, but if you were looking at something like, again, this is on the last page of your data booklet. If you're looking at something like uranium-235, has a half-life of 710 million years. So in terms of rocks, those are pretty new rocks. I mean, you could do 10 half-lives and you're at 7 billion years. So basically rocks on Earth are all going to fall in that range. You get something like potassium-40, it has a half-life of 1.3 billion years. You multiply that by 10 half-lives, you're at 10 billion years, so you're older than the universe. Very, very long half-life. And all the way up to rubidium-87, which has a half-life of 47 billion years. So just one of these things, you kind of pick what you need based on what you're trying to look at. So again, all your half-life dates, parent-daughter pairs are on the last page of your data booklet. So leave that there. I'm just gonna jump out of here for a second. I kind of stumbled onto this website. I wasn't even looking for anything to do with nuclear bombs, but I just kind of stumbled across it the other day. And I know we talked about some nuclear bombs, and I wanted to kind of show you some stuff related to how big the devastation can be. So this is obviously a map of Kelowna, and what we can do here is we can pick some bombs that are kind of common. So there's a bomb, I didn't know this, but the tiniest nuclear bomb that the United States has, they call it Davy Crockett, and it has a 20-ton sort of detonation. So remember, all of these tons are measured in equivalent tons to TNT. So the bomb doesn't actually weigh 20 tons. It has about 20 tons worth of TNT. So if I detonated that bomb, you can see this is downtown Kelowna. It's kind of like, well, I guess almost just past City Hall, probably, maybe City Hall. And you can see the fireball radius would be about the size of a building. And then the air blast goes out to these two things. So any building that wasn't made of really strong concrete would be just knocked over. And then you have your radiation zone. And in this case, 50 to 90% mortality. So half the people inside this green circle would die for sure. So that's kind of a really small bomb. That's the smallest bomb that the United States has. They have conventional bombs, so ones that aren't nuclear that can do more damage than that. So that's a relatively small bomb. So let's ramp it up a little bit. Little Boy was the bomb that they dropped on Hiroshima. So this is the bomb that ended the Second World War. Everything inside this little yellow circle on the very inside would be a fireball. Everything kind of be incinerated in that zone. Air blast would knock over everything in the red circle. And then again, everything in the green circle would be kind of irradiated. And then everything in this yellowy circle on the outside, this guy here, everything in there would receive third-degree burns. So again, a third-degree burn, it says it in the little blurb here on the side. It's a burn that's so strong that it kills the nerve ending, so you wouldn't even feel it. Burns through all 3 layers of skin, very severe burns. So that was about the size of the bomb they dropped on Hiroshima that ended the war, would take out most of downtown Kelowna and a little bit kind of out towards Rutland and out towards the Mission. The website's called nuclearsecrecy.com/nuke map. So I just Googled nuke map, N-U-K-E-M-A-P, and it's actually a pretty interesting website. You can add things in like the fallout to show how the fallout would end up going with prevailing winds and things like that. So let's ramp it up a little bit further. So that bomb, sorry, I never mentioned it. So Davy Crockett was a 20-ton equivalent of TNT. Little Boy was 15 kilotons, so that's 15,000 tons of TNT. So that's a lot. Let's go up to, this is one. This bomb almost got detonated in 1961 over the United States. So it was a hydrogen bomb, so we're getting even bigger. Pretty incredible. That's 40 or 4 megatons, so that's 4 million tons of TNT. Again, everything inside of this little circle, this yellow one in the middle, would be incinerated. Everything up to the gray one would be knocked over, and everything out to here would be burned. So that would burn everyone from lake country, well to the mission, all the way down to Peachland. Pretty crazy stuff. And does anyone remember how big the SAR bomb that we talked about was? So this was a 4 megaton bomb. The SAR bomb was a little bit bigger than that, way down at the bottom here. The SAR bomb was 50 megatons. So if we look at the devastation of something like that, the first one on the inside is the fireball, so that would be most of Kelowna. The air blast would knock over everything from West Kelowna up to McKinley Landing down to all of the mission. All of Kelowna would be essentially knocked down. I think the most amazing part of this one is the outer circle here, the thermal radiation. So 3rd degree burns from Armstrong all the way to Oliver, almost up to, like, we're talking past Big White, and then almost to Merritt. Everyone in that area would receive 3rd degree burns. So it's absolutely amazing. And that was only half as big as they had planned. They planned on making this bomb 100 megatons, that's 100 million tons of TNT, but they left the 3rd stage out. So that would be Oliver to Aspen Grove to Enderby, almost all the way to Nakusp, would be 3rd degree burns. So kind of scary, kind of amazing that we have the ability to do that, and frightening at the same time. Hydrogen can be used in fission as well as fusion because I know that the sun, a fusion reaction occurs when hydrogens wake. So yeah, we use fusion in bombs. The only way we can create enough temperature and pressure to fuse atoms together really quickly is by detonating a fission bomb first. So the fission bomb allows a fusion bomb to occur. So these bombs have multiple stages. The stages kind of happen within fractions of a second, but yeah, in order to create enough pressure, enough temperature to fuse helium or fuse hydrogen together, you need to detonate a fission bomb first. So hydrogen bombs or fusion bombs, H-bombs, require fission to get them going. And then once you've got enough energy, enough pressure, enough temperature, you can fuse things together, which creates even more devastation. So the SAR bomb, that was a fusion type bomb. If you go to the site, it's really cool. You can do things like add in fallout, and it shows like radiation clouds and all sorts of really interesting stuff. So if you want to play around with that site, you can. What are they planning to do with nuclear fusion in the thing in Europe or Germany somewhere underground? They're testing fusion technology all over the place right now, and every once in a while they get a breakthrough where basically they get some energy out. The problem with fusion is you need to get, they take protons and whip them around really fast, so hydrogen nucleus, just protons. In order to get them going fast enough, in order to get them going hot enough, in order to create enough pressure, you have to have a lot of energy involved. So you're putting in lots of energy to get the fusion going. So we can get fusion going on Earth. They put them in these big, they're kind of like donut shaped, and they're hollow on the inside, and then the plasma runs through the inside of the donut. Because if the plasma were to touch the walls, it would melt through it, because we can't contain this plasma. So we put in these big donuts. So we get it spinning around a donut really fast. Takes a lot of energy to get the plasma hot. Takes a lot of energy with big, huge magnets to contain the plasma within it. And then every once in a while, we'll get a fusion reaction going, which is normal on Earth, but it takes a lot of energy to get it going. And then we get it going for a little bit, perfect. But it took so much energy to get it going that we're not getting as much energy out as we put in. So that's kind of where we're at with fusion right now. We can achieve it on Earth, in these fusion reactors, but it takes more energy to start it than it does that we can get out of it. So yeah, that's kind of the problem with fusion right now. They call it cold fusion because we want fusion to happen at temperatures that are low enough to not melt through things. When you hear things like cold fusion, we're not talking about fusion that's cold, like ice cold. It's just fusion that's happening at a temperature that isn't like astronomically high, like in the center of the sun or something like that. So cold fusion is kind of, if we achieve fusion in an environment that we could produce in a laboratory, that's what cold fusion is. Do stars contain plasma? Yeah, plasma is another state of matter. So you have solid, liquid, gas are the kind of three normal states on Earth, and then plasma. So fire is kind of like a plasma, like the flames from fire. Yeah, it's just another state of matter. So the sun is just a big ball of plasma, essentially, yeah. So to answer your question, in Europe or Germany, there's a fusion reactor in Vancouver at UBC. It's a Tomahawk, I think, reactor. There's fusion reactors all over the place, usually at universities so they can study them. I don't know if you're thinking of CERN, the Large Hadron Collider, maybe. Ava, is that what you're thinking about? The particle accelerator in Switzerland and on the border there, where they get particles going really fast and smash them into each other and find really small particles. Yeah, so that might be, that's a particle accelerator, which is a little bit different than a fusion reactor. It's kind of the same thing though when you really think about it. We take things, speed them up really fast. But the Large Hadron Collider is several kilometers long, and fusion reactors are typically fairly small, like be contained within a building. So there you go. That's it for fusion. I wanted to get into Unit 8. So here we go. Vectors and displacement. We're going to talk a little bit about this sort of stuff. And you'll definitely need a calculator. You'll definitely need some paper today. We might not use a calculator today because the math will be pretty basic, but you'll need a calculator for Units 8 and 9 for sure. Scientific would be great. Trying to think, you guys already have scientific calculators anyway, so you'll need them for this part of the course. And your data booklet has some information we'll need on it, but we won't get to that for a few days. And today we're just going to do some basic examples, start really basic and really easy, and we'll kind of work up. So Units 8 and 9 are kind of more like a math class than they are like science, so we'll be describing motion and how things move and trying to predict where things will be, and, talking about speed and velocity and stuff like that. And there's some math involved with it, pretty basic math, but multiplication, addition, subtraction sort of stuff. So that's kind of where we're going to be. It'd be really difficult for the Units 8 and 9 material if you started in the middle. So if you start at like the end of Chapter 8 or start at the beginning of Chapter 9 and just try to take off from that point, it's going to be really difficult. So this is one of those kind of foundational sort of things where we're going to build the base today and next day, and then we're going to kind of go up from there in terms of complexity. So try to stick with me. You're definitely going to get out of it what you put into it. If you sit down and do all the questions with me, you'll be absolutely fine. There's nothing terribly difficult about it. But if you kind of just sit there and say, oh yeah, that's easy, that's easy, that's easy, and then all of a sudden we're at the end of Chapter 9, you're like, well, this isn't easy anymore. How did he get this? Or where is this coming from? So just try to do these problems as we go. I'll give you time to go through them, and it'll make your lives really easy. So it'll start really basic, which is great, and then it gets kind of harder from there. So what words do we use to describe motion? What are common words we'll use to describe motion? Anything. What would we use to describe things moving? Anything that comes to mind, because we'll probably use it. You can just throw them into chat. Let's get a big list going of words we use to describe motion. Not like if I were to tell you how to get somewhere, things like that. So speed, that's a great one. Fast, that's another one we'll definitely use. Fast, speed is a common one we'll use. Anything else? Fluid, rigid. Yeah, that's kind of going back to, I think grade 9, you talk about like viscosity and things like that. So those are some good ones. Think about giving somebody directions to somewhere. Distance, travel time, we'll definitely talk about those two, yeah. What else? If you were to give someone directions, what sorts of words would you use? Distance, direction, speed. If I told you how to drive to the mall, I wouldn't use speed. I wouldn't say drive really fast on the highway and then drive really slow on the side roads or really slow in the parking lot. So how would I tell you how to get there? So cardinal directions, north, south, east, west. Those are great ways to describe motion, and we'll definitely use those. Left, right, up, down, those are all good. Points. So yeah, we'll talk about different locations, reference points. We'll definitely do that. Things like forward, backwards. Those are kind of ones. Turn right, turn left. These are all things we're going to use today. So just a question to kind of make you think a little bit about what we're going to talk about is, if I told you something like, I live 13 kilometers from the school, from where I am teaching right now, would you know where I lived? If I said, hey, I live 13 kilometers from the school, would you know where I lived? Could you get to my house? Would it be possible for you to end up at my house? Yes or no? What do we think? Seems pretty obvious, but no. All right, so I've given you a distance. You know how far away from the school I live. Why couldn't you figure out where I lived? What's wrong with just giving you a distance? Vancouver's 300 kilometers from Kelowna. Could you get to Vancouver? Maybe, maybe not. Where is the problem here? So we're going to run into things like north, south, east, west. You don't know which direction go. And those are the exact problems we're going to run into a lot. So that's kind of one of the big ideas of this section is, when we tell people to give them directions to go somewhere, we can't just tell them how far something is. We can't say, hey, my house is 13 kilometers away. We need to give them a direction as well. So you could, Alex, and that kind of gets back to, remember we did triangulation with earthquakes. If you have 3 spheres or circles where those 3 points intersect, that's where it is. So we're not actually going to do that, but you're exactly right. 13 kilometers is a radius around the school. My house has to be somewhere on that 13 kilometer circle, but you don't know exactly where. So we're going to talk a lot about it today and over the course of the next few days. But when we talk about giving someone directions, we need to give them a distance and then a direction. 13 kilometers to the north or 13 kilometers along this road, things like that. So direction makes a big difference. There's going to be some words that are that you've heard before, but they're kind of unique to this unit. So magnitude is the size of the measurement. So that is a really complicated way of saying the 13 kilometers, that's a magnitude. That's the length of the distance or the length of the trip you wanted to do. Some things have no direction associated with them. Things like time. Hey, it took me an hour to drive to Vernon. There's no direction associated with time. It doesn't really matter which direction I drove. It's, an hour is an hour. So these things are called scalars. And then there are quantities that have a direction associated with them, and they're called vectors. So these are 2 really important vocabulary terms. that we're going to talk about. So something like, hey, my house is 13 kilometers away from the school, that's a scalar. That's measuring a distance. But as soon as I say, hey, my house is 13 kilometers south of the school, I've given you an additional piece of information. I've given you a direction. So now that distance is changed into something called a displacement, which is now called a vector. So we're going to talk a lot about scalars and vectors, and they can be really similar to one another, but just remember vectors have some sort of direction associated with them, where things like scalars, they don't. So we'll look at some examples, and we'll go from there. So again, talking about the vocabulary of physics, scalars just have a magnitude, so they just have a distance associated with them. Vectors have a distance and a direction. So if we were to look at the example here, add the two vectors below, what would the resultant vector be? So we're going to talk a lot about adding vectors, and the best way to describe a vector is to draw an arrow. And arrows are really great because they have a particular length to them. The longer the length, the greater the magnitude. And we can indicate direction really easily. If we have an arrow going to the right, we could have an arrow going to the left, we could have an arrow going up or down. These are the kinds of things we are going to be dealing with today. I've seen the movie Despicable Me, but the guy names himself Vector. Is that the bad guy? And does it have to do with this? I guess I just kind of watch it in the background while my son's watching it. Vector. Vector means different things depending on your context. So does anyone know the definition of vector kind of with respect to biology? There's a unique definition of vector in biology compared to physics. If I was talking about vectors in biology, what would I be talking about? Does anybody know? Any biology fans out there? Nobody. Vectors in biology refer to how diseases get transmitted. So if you're talking about the spread of maybe the Zika virus in Brazil right now, things that transmit the virus are called vectors. So mosquitoes are vectors, humans would be vectors. Anything that transmits the virus takes it from one place to the next. Kind of the same idea as what we're dealing with vectors, but just in a different context. So when we add vectors, we're always going to draw them tip to tail. And this is kind of something that is more important if you were to move on to physics in grade 11. Right now the questions are pretty basic and you can just kind of look at them and visualize them, but adding vectors tip to tail is a great habit to get into because once we get into a little bit more complicated type questions, it'll just make everything a lot easier. So what do I mean by adding them tip to tail? So add the two vectors below, what would the resultant vector be? We've got a lot of vocab happening here. We've got things like magnitude, vector, resultant, things you've never really heard in this context before, but it's really straightforward. So if I have a kind of like my starting point here, this is where I'm starting. And basically this question is written in terms of a picture instead of words. I could say, hey, you're at the mall and you moved 25 meters down the hallway in the mall, you went into a store, and then you moved another 10 meters down the hallway. Which store are you in front of, or where did you end up? So we use these arrows to kind of simplify things and draw a picture. So we have our starting point here, and this blue arrow is going to be 25 meters of distance was traveled. So this is your kind of like a start. And then maybe you took like a break or you went shopping in a store. And then you went an additional 10 meters. Now notice when I draw these arrows, I'm not good at it, I'll admit it, but I try to kind of draw them to scale. So I don't mean that I need to draw a blue arrow that's 25 meters long on my page, but if my blue arrow is representing 25 and my red arrow is 10, my red arrow is roughly half as long as my blue arrow. And it just really helps to be able to visualize what's going on. That's why we use arrows. And in this case, you can see I've drawn them tip. So the tip of my blue arrow here is the tail of the red arrow. So for all of these questions, we're going to end up with some sort of resultant. And the resultant is from where you started to where you ended. Now, in this case, the black arrow, which we're calling the resultant, kind of sounds like result. Think about it in terms of math. How long is the black arrow? If I started, moved 25 meters, then moved another 10 meters, my resultant in this case is 35 meters. Perfect. Yeah, so like I said, these are going to start very, very basic, and then we'll get more and more complex as things go. But the resultant is 35 meters. Is there another way I could say this? Is there something that's kind of implied with the arrow that I've used? And I guess getting back to the original question I asked at the beginning of class, if I lived 13 kilometers away from the school, you wouldn't really know where my house was. In this case, does it make a difference that the arrow is drawn in one direction as opposed to another direction? Is the direction important? I would say yes, it is. So instead of saying the resultant is 35 meters, if I've drawn a picture, it's obvious, but if I'm trying to explain it to somebody, I might want to tell them it's 35 meters to the right. Now, there's going to be no confusion here. They're going to know that I've gone 35 meters and the direction I've gone. So this is kind of where the section gets, I don't want to say it's confusing, it's not necessarily confusing, but we just want to be specific with our answers. If we have a direction to include, you'll want to include it. Let's go back to the examples here. All right, so anytime we're adding vectors, we're always going to draw our arrows. We're going to draw them roughly to scale, and we're going to draw them tip to tail. You're always going to end up with a resultant. And the resultant is where you're starting to where you're ending. So let's look at a few more examples. Add the two vectors below, what would the resultant be? So now we've got one arrow going to the left, which is 100 meters per second long. And we have an arrow going to the right that's 30. So you can see how the red arrow is about a third as long as the blue arrow. And we want to draw them tip to tail. Does it matter which one we start with? I don't know. Let's find out. I'm going to jump back to my OneNote here so I can actually draw on this. All right. I'm gonna just start with the blue arrow because that's what I did with the previous question. I'm gonna have my starting point. Now this would be like saying, we don't really know what meters per second means, or meters divided by seconds. Can anyone think of what that might indicate? It's a unit we haven't used before, but if you think about it, what does that really mean? Meters every second. If I told you I was traveling 100 meters in 1 second, what would that be? Or if I told you I was traveling 30 meters in a second. So we have a measure of time, but if I wanted to say time, would I say just 100 seconds? What's the difference between 100 seconds and 100 meters every second, or meters per second, or 30 meters per second? Why not just say 30 seconds if they both measure time? So Abby, you've written in time to distance. Do we have a common word? You're right, but do we have a common word that we will use to describe how far I've traveled in a given amount of time? Once I say it, you guys are going to be like, oh, that kind of makes sense. Meters per second is a measure of speed. Think about the speed limit on the road. It's 50 kilometers is a distance every hour. If you travel to Vancouver on the highway, the speed limit's 120 kilometers every hour. 120 kilometers per hour is a distance over a given time. So when we talk about meters per second, it's just the speed. So there's 100 meters traveled every second. That's a pretty fast speed. So this arrow goes to the left. That is 100 meters per second. And then I'm going to draw my vectors tip to tail. So my red arrow is going to start where my blue arrow ended. And it's going to go that way at 30 meters every second. So this is where things get a little bit tricky. I'm going to draw on my resultant. Remember, this is where I started. I had a difficult time writing start today. Start. And it turns out that this is where I've ended here. So my resultant is from where I started to where I ended. Started there and I ended there. So what is the length of the black arrow, or what I'm calling the resultant? What's the length of this? And does it have a direction associated with it? If I traveled, if I was traveling at, let's say I'm flying in a plane, traveling at 100 meters per second, and the wind is pushing me back at 30 meters per second. How fast am I actually going? That's kind of what this question's could be asking. Or if you're in a boat on a river, you're traveling 100 meters per second, which is really fast for a boat, but we'll go with it. 100 meters per second on your boat, and the current in the river is pushing you back at 30. So what is the resultant? Well, it's exactly 70, you're right. Anna. You're right, Anna. So we have the resultant. Our resultant is going to be 70 meters every second. And then we want to be specific as to which direction the black arrow is pointing. So is that 70 to the right, the left, up, down, forwards, backwards, north, south, east, west? We want to be really specific as to which direction the arrow's going. So in this case, we have 70 meters per second, and our result in the black arrow is pointing to the left. That's all we really know about it. So the resultant is 70 meters per second and to the left, or just 70 meters per second left. And that is describing this kind of black arrow that we had here. All right, so the first question we did, we have both of arrows going the same direction. The second example, we have one going to the left, one going back to the right. We needed to add them together. All right, example 3 is actually a bunch of examples. Hopefully you can take the ideas that we just used and kind of put them together. One thing that is a little bit confusing even for me is I don't love how the book has written little negative signs in here and then used an arrow going to the left. So the negative, we haven't talked about signs yet, positive, minus signs, but we have these little negatives in here, which is kind of confusing. So just ignore them for now. What they're going to indicate is that you notice every time I have a negative sign, the arrow is going the opposite direction as the other arrow. So we'll worry about signs later. So for now, just think of it in terms of the arrows. It's going to the right, going to the right. This one's going to the right, going to the left. The right and the right, the right and the left, the right and the left, up and down, throwing a curveball at you. So see if you can draw these vectors tip to tail, and for each one, figure out what the resultant is. And remember, the resultant needs to have a direction associated with it. They don't have any units, you're right. So not a big deal, no units there. We can just say right, left, up, down. They could be speeds, they could be distances, they could be, I guess they couldn't be times because time doesn't have a direction. So don't even worry about direction. Just say, you know, up or down or left or right. 10 to the right, 10 to the left. So this is kind of what I was getting at before. It seems really basic, drawing these tip to tail, but it's a good habit to get into, and you will make far less mistakes if you draw vectors tip to tail. Even if they're really basic and you just look at them, it's kind of like when you do math in grade 10, sometimes we ask you to add quantities together, even though you're really good at adding. Well, you know how to add, but it's worth it to just, you know, write it down anyways, because you're going to make fewer mistakes that way. So I'm sure you guys have probably done some of these already, but I'll give you maybe just like a minute. I'll just sit here and twiddle my thumbs. And you guys can go through those and just see if you can draw them and come up with an answer which includes a direction. Remember, the direction's important for now, from now on in physics, in Science 10. All right, I'm thinking you've got some, if not all of these done. I have the benefit of being able to use lots of colors. You guys may or may not have the option of using colors at home. It's not important that you do use different colors like I do. I'm just using colors to kind of distinguish between the different arrows. So definitely not important. I'm going to try to do this to leave myself as much room as possible so I get them all in here. So the first one here, think about drawing like a dot to start these. And the first one is 5 to the right, and then another 5 from there. So I have 5 and another 5. And from the start to where I finished has a length of 10 to the right. So that's it there. That's all you're doing. All right, the next one, so I could give these some letters. Letter B is starting here, looking at my first arrow, it's 5 to the right, and then I have 5 back to the left. So if I started and I ended, I'm starting and ending at the same point. So my resultant in this case, there's actually no arrow for the second one. It's just 0. It's kind of really weird. And I don't have any units, so this could be meters per second, could be meters per second squared, it could be kilometers. I don't know what it is. But when I have 0, I can't really associate a direction with that. There's just no direction to go with it. So it's just 0. It's not 0 to the left, it's not 0 to the right, it's just 0. It's kind of a really weird idea to kind of think about. The third one we'll call C. So my first arrow here is 5. I have my starting point. I have 5. And then my red arrow is going to be twice as long. That's going to be 10. So if I start here and I end over here, I've traveled 15 to the right. Guys, hopefully you're recognizing patterns here. Slide D in up here. So my first one for letter D is, I'm starting here. I'm going to go 5 to the right. And then I'm going to draw my vectors tip to tail. And my second arrow is actually going to go past where I initially started. So if I were to draw a resultant, if I started here and I ended there, that's 5, and this is to the left. So that's a bit of a tricky one, letter D. 5 to the left. This one we'll call E. All right, so I'm traveling 5 to the right. And then from there, I'm going 15 to the left. So remember, this is where I started, and I ended right there. So that is going to be 10 to the left. We'll do the last one. Things going up and down are no different than going right or left. So I'm going to start. I'm going to go up 10. And then my second arrow is going to go down 5. And if I think about where I started to where I ended, that's going to be 5 up is my resultant. All right, how do we feel about those types of questions? Are we all feeling okay? Have I lost some of you? Does it seem pretty straightforward? Perhaps a little bit too easy, or is it kind of like a little bit complicated at this point right now? How are we feeling? I've got a thumbs up and I'm good. 2 people are doing okay. Yeah, Taylor, that's a huge part of what we're going to be doing. A lot of these things are going to be different directions. And we'll see some questions today where I've got like 2 or 3 things going up and a couple things going down and maybe even some left and right, which can make it complicated. But that's why we use arrows to kind of preserve the direction. So it's important that we use them and we can add things that are going in different directions. So it'd be kind of like, hey, Taylor, I want you to walk forward 5 meters, and then I want you to walk backwards 2 meters. Where did you end up? How far are you from where you started? Or if you're in a boat going down a river, and the boat's going 5 meters per second, and the river is going at 5 meters per second, how fast forward are you going? Or maybe even a more crazy example, if you're in a boat and you're going upstream, and the stream's going past you at 5 meters per second, but your boat's going 5 meters per second, those are going to cancel each other out. You're not going to be really moving anywhere. Even though your boat's running, it's moving, but the water is pushing you back, and you're pushing at the same rate as the water. So this is kind of what physics is all about, describing motion. We start with really basic sorts of ideas, and then we can get into really complex things. If I throw this pencil off a cliff, how long does it take to hit the ground? You can use some formulas to calculate things like that. So that's where we're going to kind of build up towards, those types of questions. But we're going to start at a very basic level. All right. The first ones, we had everything that were going either left or right or up and down. What happens if we have vectors that are going in different directions? If I say, give you directions from my school, travel north for 5 kilometers, and then you need to travel west for 3. Where do you end up? What happens if you're drawing vectors that are going in different directions? If I say, hey, go 5 kilometers an hour south, and then go 3 kilometers an hour to the right, where are you going? Which direction are you headed? You don't have these in your booklet. I'm thinking the notes for this unit, for Unit 8 and 9, are kind of like the ones for Unit 7, where it didn't exactly go with the notes. It was just kind of some questions that you had to do, and then there was some, fill in the blanks. There's like a table, scalars and vectors and things like that. So they don't match up perfectly. The last ones were in the notes and these ones aren't. Yeah, sorry. Maybe if you have just some room on the bottom, or you can grab a blank piece of paper or something like that. We'll go through some of these and we'll see how they can get a bit tricky. All right, I'm going to do them the exact same way. So I'll draw this one, first one really big, and then we'll go from there. So I have some sort of starting point. This is this first one. So I have this starting point. I'm going to draw my starting point right here, and it looks like it's 5 to the right. So I'm going to go 5 to the right. And then instead of going further to the right or back to the left, I'm actually going up. So when I draw my vectors, I draw them tip. So I have the tip of one vector is the tail of my second vector. And I'm going to go up 10. Now again, I don't have any units, so that's okay. Now, drawing my resultant is always the same process. So before, when I drew my resultant, it was from the start to wherever I ended up. And that's what I'm going to do here. The start was there, the end was there. How long is my resultant in this particular example? Or can you think of a way I can calculate the length of that arrow? Now, direction is going to be a little bit difficult to describe because I'm kind of going up and to the right. You could say something like that, but it's kind of, probably a grade 11 concept. We use the Pythagorean theorem. You're right, Abby, we do. So we have a right triangle, if you can imagine that. There's our little right angle in the bottom corner. We have a right-angled triangle. We know that we can figure out any missing side on a right-angled triangle as long as we have 2 additional sides. So I'm going to go a squared plus b squared, c squared. It doesn't matter what a and b are. I'll call a 5 because that was the first one I drew. A squared, b squared is c squared. So I'm going to have 25 plus 100 is equal to c squared. Add those together. And then I'm going to take the square root of both sides. And I don't know what the square root of 125 is off the top of my head, but I do have a calculator that has that information for me. So I'm going to take the square root of 125, just plug it into my calculator, and it tells me that that is 11.18. So we'll just call it 11.2. Now, I'm hoping you guys are experts with the Pythagorean theorem by now, but if you're not, that's okay. So we haven't done any really difficult math in a while. So the beauty of me teaching you both math and science is that I know we use the Pythagorean theorem an absolute ton of times in math. So I'm confident that most of you guys are okay with that. I could be wrong, but I don't think I am. So there you go. That's how you're going to do these questions. I'll just give you, I don't know, there's a few questions, 3 questions there. I'll give you a few minutes to do each of those, and then we'll see what type of answers you ended up with. The last one's a kind of a tricky one. See if you can figure that one out. If you follow the same steps that we've been doing, you should be able to do the last one. Can we give a direction? That's a good question. Not in grade 10, you won't need to. The direction, we usually use kind of cardinal directions to describe it. That would actually be, what would that be? That would be north of west. But we're not going to calculate the angle or anything like that. So more of a grade 11 concept. But if you can use the Pythagorean theorem to find the length of the resultant, you're doing great. That's kind of where we want to end this now. So just give you, I don't know, 5-6 minutes. No, you probably won't need that much. 5 minutes, a bit generous, to do those last 3. And the last one's tricky, but I think you guys can do it. So I'll give you a couple seconds to do those, and we'll come back and we'll talk about them. All right, I'm excited to see which who got the last one. What about the second one here? I kind of jumbo sized this a little bit, so I'm just going to zoom out a bit. The second one here. Did anybody get an answer for the second one? I'll definitely go over all of them. I'm thinking the second one's pretty straightforward because it's really similar to the first one, but the resultant will just be in a different sort of direction. So let's 11.2, perfect. So the second one, B here, is instead of going to the right and then up, I'm going to go up and to the right. Which ends up being the exact same question. So I'm going up 10, and then I'm going to the right 5. And the resultant is exactly the same. It's kind of like if I told you, go forward 5 meters and then turn left, or if I say, hey, go left 5 meters and then go forward 10. You're going to end up at the same spot. So both these are the exact same. So that's A and B. C is a little bit different, so I'll do that one real quick. Maybe some room over on the other side. We'll call this guy C. All right, so I'm going to start here. I'm going to go up 10, and then I'm going to go to the left 10. Does anybody have a number for a resultant for letter C? What I'm calling C? So I started here and I went along there. Taylor got 14.2. Does anyone agree or disagree with that? I'll break out my Pythagorean theorem, and then if anyone wants to agree with that. So we have 10 squared, and 10 squared is 100 and 100. C squared, 200 is equal to C squared. And then I take the square root, both sides. Square root of 200, I'm going to just trust you guys. I'm not even going to break out my calculator. 14.1 sounds good enough for me. So this resultant is 14.1. Perfect. Everyone's on the right page. Well, everyone who's written something in chat, that's a good sign. This last one is tricky. It's all kinds of tricky, but I'm thinking if we follow the rules, we can do it. And of course, we've never drawn 3 arrows together yet. And now I've given you 2 directions to deal with, so it's kind of really complicated. So let's go. Let's see how we do. I'm going to start here, and I'm going to go down 5. And then I'm going to write in a number there, 5. And then I'm going to go to the right 5. And then I'm going to go up 10. And I draw my resultant. Is the last one 7.1, or is it not a triangle? We can make a triangle out of it, and you can always do that. So my resultant is going to be from my start to my end. I don't really like that arrow. Try that again. There we go. All right, so what I'm going to do is I'm going to make a triangle out of this thing. I'm going to draw in some like dotted lines here just so you guys can see where my triangle is. There we go. Got a little right angle here. So the base of my triangle is 5. What about this little bit here on the side? I know it's not 10 because the whole green arrow is 10. What's just that little bit that I have up at the top there? How long is that? Well, I went down 5 and then I went back up 10. So this little bit in here is 5. Perfect, Taylor, you got it. All right, so I can write in a 5 here. So if I have my Pythagorean theorem, I kind of have to decipher a little bit where my triangle actually is. I'm just kind of adding one in there. So I'm going to get 5 squared plus 5 squared, 25 plus 25, c squared, 50 is c squared. And then I'm going to take the square root of both sides. Square root of 50 7.07. So Ava had it. We'll call it 7.1. So well done, Ava. That was a hard one. How did we do on that one? Did a few of us get it? Did we miss it? It's kind of weird how we draw it. Another way you can do it is you can do all the ups and downs first, and you can do all the lefts and rights second, and then you can get all your lefts together and all your rights together and figure out what the resultant is going left, right, and then you can figure out all your resultants going up, down, and then you can make a triangle with those and then find your resultant. It's the same process. Sometimes it's even easier to do than what we've done. Okay, well, that's good to know. Because obviously, Anna, it's the first time you've seen something like that. So if you think, you kind of understand and can follow along, that's good. No worries, Taylor. Glad you're back. All right, there's a couple more sort of idea things that I want to go through, and then we'll do a few more examples. And then we will finish off. So I know I usually do a break after about an hour, but I'm thinking we can just kind of power through this. If I'm not mistaken, there's only a few more examples and then we're done. So we'll just, instead of, dragging out the morning, we'll just finish a little bit early. All right, so we're going to talk about some more vocabulary words. So far we've talked about distance, we've talked about magnitude, direction, scalars, vectors. These are kind of all words, resultant, all words that you've heard before but never really seen in this context probably. And we're going to make it, I don't want to say confusing, but we're going to use words that you've kind of always used to mean the same thing, but in physics, they mean different things. So we're going to talk about distance and position. And we're going to have a few sort of words that pop up that you're like, well, I've definitely used that word before, but now it kind of has a specific meaning. So distance is a scalar, meaning it doesn't have a direction. So that was kind of like going back to my house is 13 kilometers from the school. That's a distance. There's no direction associated with it. It'd be really difficult for you to find my house just knowing it was 13 kilometers away from the school. So the example here, a person ran 400 meters. There you go. That's a distance. I know how far they ran. I don't know where they ended up. I don't know what direction they ran, but they ran 400 meters. For all I know, they did a lap of the Apple Bowl, 400 meters. They started where they finished, or they could be 400 meters away. I just have no idea. That's a distance. A position is a distance with respect to another thing. So this is kind of like the resultants we've been drawing. We can say, your position is so far away from the Apple Bowl or something like that. So example, the school is 3 kilometers east of my house. That's easy to understand. 3 kilometers is how far you've gone, which direction? To the east of your house. That's kind of where we're going with distance and position, why they're different. So SI is Systématique Internationale, French consortium, does all the units for all of the world, and distance and position are both measured in meters. The only difference between them is that position will have a direction associated with it. This is not in the data booklet, the learning guide. I didn't print it off. I just looked at it quickly, and it seemed like it was kind of one of the learning guides where you just kind of go and some of the definitions kind of pop in and out, and there's some examples that maybe aren't there and are there. Is anyone else having some issues with that, or are we okay in terms of the learning guide? Is Is anybody else finding this stuff in the learning guide? Maybe if you had a page, you could throw it into chat or something like that. I didn't bring the learning guide with me. I don't even think I put the learning guide into OneNote, which I usually do. Nobody's chiming in, so everyone's asleep, I suppose. All right, so there's a little image down here at the bottom. I just want to talk about it real quick and then, okay, thank you, Shayna. So it's not just you, Taylor. It's definitely not in there, which is okay. You just take it in. All right, so let's say your house and the store were perfectly west and east of each other. So let's say I was at my house and I drove to the store. What is my distance I've traveled when I'm at the store? Oh, I have a laser pointer. Let's use that. What is the distance I traveled? So I started at home and I ended at the store. What's the distance I've gone when I'm at the store? And what is my position when I'm at the store? What do we think? Are my distance and position the same thing when I've gone from my house to the store? Or are they different? So distance. Distance first, 10 kilometers. That makes sense. I've gone from here to here. That's 10 kilometers. That's a good distance. And if I were to talk about a position, Abby, I think that's what you're referring to. It's 10 kilometers east. Now, we could be even more specific. 10 kilometers east is fine, but you could say 10 kilometers east of my house. Perfect. Okay, now I've bought my groceries at my store. I've driven back home. So how far have I traveled? What distance have I gone to go from my house to the store and then from the store back to my house? What's my distance traveled? And when I'm at home, what's my position? That's a bit of a tricky question, my position when I'm at home. So, Taylor, you've written in a position there, 10 kilometers west of the store. That's good. What's my distance traveled, though? How far have I gone? And is there another way to represent my position? Do I have to say 10 kilometers west of the store, or can I represent that a different way? Those are some tricky questions for a Monday morning. All right, so imagine I started at home, drove to the store, went back home. My distance traveled is 20 kilometers because it was 10 kilometers to get from my house to the store, another 10 kilometers to get back. So 10 and 10 gives me the 20. My distance travel is 20. When I talk about a position, I could say I'm 10 kilometers west of the store, or I could say I'm 0 kilometers from my house, which kind of is a really strange way to write it, but it's true. I'm giving you a position. How far am I away from something? If I left my house, drove around town, and then ended back at my house again, how far am I away from my house? So a position just needs to have, a distance away from something. So I could say, lots of different ways to represent the same thing. So it's a bit of a weird sort of idea. All right, so those two we looked at before were distance and position. Now we're going to talk about distance and displacement. Now again, two terms you've probably heard about, but now have new meanings. So displacement describes the straight line distance and direction from one point to the other. And displacement is equal to the final position minus the initial position. Displacement's the change, and we'll look at a different way to describe that here. But this kind of definition of displacement, displacement is equal to the final position minus the initial. This is a really complex, confusing way to describe displacement until we actually get into the next unit when this sort of definition will make more sense. But for now, it's just kind of a bit strange. So we'll talk about it a little bit, but don't be too overly concerned about it. Some questions here. If you start at your house is the most correct way to say 0 kilometers from the house. I wouldn't say that there's any more correct way than another. They're all sort of relative, right? They're describing the same thing, but just in a different way. I could say, if I was trying to describe where I am, I could say I'm 10 kilometers, not 10 kilometers, I'm 5 kilometers south of the mall. You'd know where I was. I could say I'm 300 kilometers northwest of Vancouver. Northeast of Vancouver, makes more sense. They're both describing my position with respect to something. They're both correct, not one is more correct than the other. So usually we'll have a picture, we'll have some sort of reference point. In the previous example, we had the house and the store. So you can use either one of those. Now, we're going to end up seeing a few pictures like the one here, where they give you a distance law on the bottom, and then they have different times sort of in there to figure out what's going on at each of those points. Sorry, Abby, I just saw that you asked a second question here. So displacement could be less than distance. It can be, yeah. Think about it this way. If I started at my house, I drove around town, maybe I went out to Tim Hortons to get some coffee and then to save on foods to buy some groceries, and then went to the dog food store to grab some food for the dog, back home. How far did I go? Well, my distance was, maybe 5 plus another 5 plus another 5. So I traveled maybe 20 kilometers on that trip. But what was my position? Well, I started at the same spot, or displacement, I should say. My displacement, how far am I away from my house? Well, I'm 0. I started at my house and I ended at my house. My displacement is 0 meters. But the distance I traveled was 20. So this is why it kind of gets a little bit confusing. Depending on where I go, my displacement and the distance could be the same, or they could be different. Just depends on how far you are from where you started. Generally speaking, though, displacement's going to be smaller than distance. Generally speaking. All right, let's jump back. Did I lose it? Did I just completely lose it? There it is. All right, so if we look at, can I do number 10 on page 2? I can. I don't know what it is. I'll have to find it and load it, but I can for sure. I'm just going to finish this off. It might even come up in the next few examples there, Taylor, so we'll get to it possibly. And if I don't, then I'd be happy to do it. So this little fella here is skateboarding. At 0 seconds, he's at 0 meters. 2 seconds later, he's at 2 meters. And then 5 seconds after that, he's at 7 meters. So we can describe his distance traveled. In 2 seconds, he's traveled 2 meters. In 5 seconds, he's traveled 7 meters. And we can describe his displacement. How far is he away from where he started at 5 seconds? Well, he's traveled 7 meters. What if I wanted his position or displacement from the fire hydrant to the sign? How far has he gone from the fire hydrant to the sign? I don't have to always talk about the tree to the sign. I could talk about from the fire hydrant to the sign. What is his displacement between these 2 points from the fire hydrant to the sign? Well, he started at 2 meters and then he ended at 7. So how far did he go between the fire hydrant and the sign? Well, that was 5 meters. So his displacement from here to here was 5 meters. What about from the tree to the sign? Well, that's now 7 meters because we started at 0 and then you went to 7. What are you really doing when you're calculating that? You're actually doing subtraction. And what I mean by that is you're saying, okay, he ended at 7 and he started at the tree at 0. So 7 minus 0 gives me 7. But if he started here and I want to know his displacement from the fire hydrant, well, he started at 2 and he ended at 7. So in your head, you're going, okay, well, that's 5 meters because each one of these is 1, 2, 3, 4, 5. Or you could go 7 minus 2 and you could end up with 5. So in your head, you're probably doing subtraction even though you're not really. Let's just see what is left here. All right, I'll do a couple more and then we'll just call it. It's an hour and a half. It's been a long time. All right, so let's do a couple of these examples and then we'll see how we're feeling, and then we might have to finish some of this tomorrow. All right, that's not where we are, not where we are. There we are. All right, distance versus displacement. We'll do a few examples. And the one in the notes here is a car drives 3 kilometers north, then 2 west, then 3 south, then 2 east. What's its distance and what's its displacement? Now, I'm a very visual person. When somebody gives me directions like, hey, go this way and then that way and then turn it this and go there, it kind of just goes in one ear and out the other. I can't process things through audio. I need to see them written down. And in my experience, students do very well when they draw pictures. So I've written in giant letters here at the bottom, hint, always draw a picture. So do that, draw a picture. When I teach Physics 11, I give students a mark for drawing the picture. I'm not talking like, do you have beautiful flowers and is your butterfly's wings symmetrical? Not things like that. Just arrows and dots. That's what I'm talking about here. So, oh, it's similar to the learning guide? All right, well, we'll just go through it and we'll see how we go. All right, so like I was doing before, I was drawing pictures with arrows, and I'm going to continue to do that. So I'm going to have some starting point. Let's see if I can get this all in here. A car drives 3 kilometers north. So here's my start. Might regret writing that there. So I go 3 kilometers north. So north is up. And then I go 2 kilometers west. And then I go and then I go 3 kilometers south, so I'm back to there, and then 2 kilometers east. What is the car's total distance traveled and the displacement? Whew. All right. Distance is how far I went. So this is kind of like if you've driven a car recently or if you've looked at a car. You have something called an odometer on your car. And your odometer on your car doesn't care if you're going forwards or to the left or the right, you turned here, you turned there. It just counts up. The wheels are spinning, the odometer is counting up. That's what distance is. How far did you go? So in this case, the total distance traveled was, I started and then I ended at the same spot, which was a little bit inconvenient, but we'll figure it out. So I went 3 kilometers, and then I went another 2 kilometers, and then I went another 3 kilometers, and then I went another 2 kilometers. So how far did I go in total? Well, 3 plus 2 is 5, plus another 3 is 8, plus another 2 is 10. So my distance traveled was 10 kilometers. That's how far I traveled. That's the odometer reading on your car. You went up 3, you went left 2, you went down 3, you went to the right 2. My displacement, maybe I'll do this in green, is how far am I from where I started? So from the beginning to the end, from my start to my end, how far am I away from my starting position when I finished? The displacement is the same as the resultant. They're the exact same idea. Yep, they will mean different things. The resultant, we can talk about the resultant in more than one dimension, so like we can go up, down, left, right. Generally speaking, displacement will be on like a horizontal line sort of thing. So how far am I from where I started? If I start and end at the same spot, I guess kilometers is the units we were using. So the displacement in this question is 0. My distance was 10, but my displacement was 0 because I started and ended at the same spot. All right, maybe we'll just do this one and we'll call our day there. A child walks 3 meters north, 7 meters south, 2.5 meters south, and then 5 meters north. What is their displacement? All right, here we go. I'm gonna start here at the blue dot. I'm going to do it step by step. When I say draw a picture, I don't need to draw the child and the trees that are around him and the grass on the lawns that he's passing. I'm just drawing arrows and dots. So a child walks 3 meters north, and then he walked 7 meters south. This is why it's important to try to draw your diagrams roughly to scale. It'll make your life easier in the long run. I'm gonna run out of room there. That's 7 meters. And then he walks another, or she walks another 2.5 meters south. So 7, that's 2.5. Make sure to include my units. And then 5 meters north. What is their displacement? So how far, displacement is how far are they from where they started? So displacement's kind of like from here to there. What is that distance? What do we think? This is my end point here where I ended up. This is where I started. What is the displacement? How far am I from where I started? Is there an easy way to do this? Anyone think of it? There's, I guess there's no real right way to think about it, but can you do 3 minus 7 minus 2.5 plus 5? What do you end up with there, Abby? Let's check it out and see if it works. And then maybe if somebody, I'll try to like dissect the diagram. So Abby suggested anything going up is positive, anything going down is negative. So 3, then we went south 7, then south 2.5, and then north 5. What do we end up with there? I'll maybe kind of look at the diagram really closely here. So I went up 3 and then I went down 7. So that's kind of, I basically have lost, I guess I've gone down 4 here. Going down 4, because that is what's left, and then I've gone down another 2.5, then I've gone up 5. So I'm going to think of it as going down 4, and then down another 2.5, and then up 5. So I'm going to go down 4, Then I'm going to go down another 2.5. So I'm going to add 2.5 to that. Then I'm going to go up 5. So if I go down 4 and down 2.5, that's 6.5 I've gone down. And then I've gone up 5. So I'm going to subtract 5. And again, I'm up with 1.5 meters from where I started. If I go 3 minus 7 is negative 4. Minus 2.5 is negative 6.5. Plus 5 is 1.5. So this is negative 1.5 meters. And that's the same thing I got here. We end up with these kind of like different signs. So what's going on? Well, mine, I didn't really indicate a direction. And here, this negative sign is actually indicating a direction for us. That's why we ended up with that negative sign. So in my diagram, it's easy to see that my arrow is pointing down. That's what this 1.5 is referring to. In my calculation, if you just do it like you guys chose to do it, which was completely fine, you do end up with a negative, which just means in this particular question, it's going south or down. So I could write 1.5 meters south or negative 1.5 meters. They both mean the same thing. And yes, that's how I would suggest you guys do it. Why do I insist you draw a picture though? Well, if you were to go 3 minus 7 minus 2.5 plus 5, you end up with negative 1.5. What does that really mean? If you've drawn a picture, you can see that you've started here and then you've ended just a little bit below where you started. So it's really obvious in the picture to figure out exactly what's going on. So that's why the picture is important, and the picture goes along with the math. If you want to add your norths and souths, or add your norths, add your souths, then take the difference between them, that's fine. That is how you do the question. But the picture adds clarity to it. You can see that you've ended up just a little bit below where you started. So that negative sign makes sense. Abby, both answers are the exact same, which is kind of a funny thing in physics. So you could write negative 1.5 meters, or you could write 1.5 meters south. They both mean the exact same thing, which is the really kind of weird, interesting part of physics. We'll talk a little bit more about it later on. Negative signs indicate direction in physics. So both are the same. 1.5 meters south or negative 1.5 meters, both the same. Doesn't matter. Both are going to give you the correct answer. We'll look more into it later. So I don't have the learning guide with me. I'm just going to jump into the class here and grab it. And then we'll see how far we finished. I'll continue on with this stuff next day. All right, Unit 8 Learning Guide. Taylor, you asked a question number 10 on page 2. Let's have a look at that. Can 3 parallel vectors unequal magnitude add to 0? It's a good question. Draw a picture for that for sure. Can vectors different magnitudes and directions add to 0? Show with a vector diagram. Delta symbol we didn't really get to yet. We did these in class. And this is really similar to the question we just did. 4 meters north, 7 meters south, 2.5 meters south, and 5 meters north. So see what you can do there. Maybe now that I've done that example, Taylor, you may be a bit more prepared to do that. I'll maybe take it up next day. And if you guys have some questions with this sort of stuff, yeah, so we should be okay up to velocity. I'll do a few more questions next day in class, following through the notes. And if you guys go up to the velocity section, you should be okay. We haven't talked about velocity yet. So just kind of bounce back and forth between the questions because we have not learned it all. I'm thinking you guys have learned it all, to be honest. There'll be a few questions where you'll end up with maybe not seeing an example that's really similar to it, but if you use the sort of the concepts we talked about, you should be okay. I apologize for taking so long today. No, we don't normally take quite as long without sort of breaks, but hopefully you guys are okay. Just try. That's all I'm asking you guys for now. Try to do everything you can up to the end of the velocity, or up to the velocity, not to the end of the velocity. So you're going just into the middle of page 3. Do what you can. I will go through the rest of the questions in the learning guide or in my notes, which aren't the same as the learning guide, but similar. I'll go through the rest of the questions at the beginning of next class. If you guys have any other questions from the learning guide, I will go through those as well. And that's kind of where we're at. So I want you guys to just try. That's all I'm asking right now is just try. And if you are doing okay, then great. If not, we'll spend some more time on it next day. That's kind of it for now. Thanks very much. I will see you guys on Wednesday. Have a great afternoon.